So let's take a minute and think about how we're going to analyze our beam, why we want to analyze it. The primary question is, how deep does that beam have to be, or how wide? What are the basic shape dimensions of it? And it's critical to us as designers not to make sure that it's just strong enough, but to make sure that it also looks attractive, so that it doesn't look too thick or massive. To be as small as possible, to be as elegant as possible, to have the desired shapes that we might. And that's really that's what our discussions are with the structural engineer. He's going to make sure that it holds up and meets the criteria for structure, but we will also want to help him make sure that the determination achieves our goals, which is the aesthetic value of that exposed structural steel. So let's just take a look in. I've done these calculations for a sample, and I've left it blank in many ways just so that you fill in your own ideas about data and information here. But I'll just tell you the general thinking. We have to figure out what our load is, what our tributary load is. And that's the live load plus the dead load is the total load. And so we can make some assumptions. It could be the live load would be a snow load. And in Chicago, looking that up on a chart, you'd find that to be about 25 pounds per square foot. And then you could assume maybe the same amount as a dead load to give you a total load. And to do our calculations across this beam, which I'm showing you both the beam here and then what it would look like when we go into our software and do the calculations, this idea of that implied load, this uniformly distributed load across this beam, and then we need to figure out what that'll be, what kind of data we're going to input. So our load per foot of beam is equal to our total load divided by the length of that tributary load. So it's just a matter of dividing out that length of 65 feet, or in my case 48 feet, in order to get that idea of the load per foot. And then in order to get that into the right units, we want it into kips, which is thousands of pounds. So the load per foot in kips is the load per foot of the beam divided by 1,000 to give us kips. So with that in mind, we're ready to now start looking at this idea of an analysis of this. So I'm going to bring over a web resource that you can go to. Let me just close this down a little bit so it fits completely on the screen, or best I can. Oops, lost it. Hold on, let me grab it back. And it's webstructural.com, and we'll go to Start Designing. And it takes us into a beam, which is the analysis that it allows us to do. And you can see it's already somewhat set up. It has a a beam, a continuous beam pinned at 3 points. So we kind of want a similar condition. And it has a uniformly distributed load, and it also has a point load. So let's just start modifying this condition. And it's very easy to do this. All we have to do is select the item. So if I click on this, it'll open up and it'll say point load, and we're just going to delete it. And now that's gone. We want our uniformly distributed load to go over the full span. But before I do that, I'm going to close this off, because what we really want to do is we want to change the span to whatever span you think it should be. And in my case, I'm going to use 24 feet, which is not the right number for the structure we built, but it's a start. And now we can adjust that uniformly distributed load. And now that we know my spans are 24 by 24, the total span of that unit, or the total span of that load, is 48 feet. And I'll make an assumption. Let's put in, I'll put in 5 kips per foot and save that. And now you notice we have that uniformly distributed load. But we have a pin condition and a pin condition, and we know we don't have a pin condition at this end. It's free. So actually you just click on this, it'll go to fix. If you click on it again, it'll go to free. This one will stay pinned because it's over that point support. And this one I'm going to say is fixed because it's tied off to to the continuous run of that beam. And I don't want it to be free. I want it to be fixed. And that's my assumption. That would be the assumptions that I would say I thought about when I start discussing with the structural engineer. And I wouldn't be at all surprised if he said that was the wrong way to assume that, which is fine because it's just us having that discussion and a chance for learning. So with that in mind now, we're actually ready to calculate to find out if we could use a W8 by 15. So go ahead and calculate it. And you'll notice that it gives us all this information telling us how it failed. And, this is all very, the failure is just very useful information. If you look, the deflection of this end of the beam is L over 10. It's deflecting 473 inches. So we know that this is way too weak a beam, an 8-inch deep I-beam. So I'm going to go ahead now and just start to pick something that's much more reasonable as far as the depth of a beam. So let's say I'll go up to, we know the beam that we selected in ours, I think we set it for 4 foot. So I'll maybe set ours for 33 inches because mine is different. I'll calculate that. We can look at what's happened now with the changes. So it's still failing in bending. There's too much bending forces on it, and it's still failing in deflection. It's managing to survive in shear, though. So we're getting close. If you notice the L over 170 deflection, it's now deflecting only 3 inches. Now, that actually could be an okay case in the fact that this isn't a floor system. So this might be an acceptable amount. L over 170 may be an acceptable amount of deflection. I don't know. But that's the determination by the structural engineer. So we're going to have to beef this up a little bit more. So let's say we'll go up to we'll go to 36 by, let's say 194. I'll calculate that. We're still not there yet. Let's try to add some beef to it. So if you'll notice, this is 194 pounds per foot. So let's say we go to pretty heavy, a 36 by 400, and calculate it. And now we have actually too much. We have L over 760, so we could actually lighten that up a little bit. So I'll go back to the chart, and let's take it back to 331, calculate that, and we managed to hit all the criteria, and we're actually still over criteria. So we could come back and continue to whittle this down and wait until we get close. And I'll just do one more. It's 330, so let's go to and calculate that. I think I went up 3 inches. I think I started with 33. So we're still stout enough. We're well above that, and we could assume our depth to be 36 inches. Let's say we wanted to hit another goal. Let's say we wanted to go to 33 inches. So we could go to the stiffest 33 and see if that would work. And it still works. So we managed to trim 3 inches off the depth and still can support our deflection. I'll go down to, that's 33 by 387. So maybe we can go down in weight. And we're still meeting criteria. So I was really over designed there when I jumped to 36. So let's try to get this to the point where, all right, so I'll just leave it at that. You could see that you could, for the sake of instruction, you can see how we're still well above the maximum deflection level, and we're meeting all of the other criteria of this. So we now have this idea of some kind of a suggestion for the size of the beam that we would want to use. And I would, in your experiment, take this down to as light as you can meet up with the deflection criteria requirements of this case. So when that's done, I would want you to take screenshots, as I've done. So I have a snippet tool, and I don't think I'll drag it onto the screen, but if you just, Google or you actually search for the snipping tool, you can go ahead and take a screenshot of that, and then import that as an image back into your document, as I've done. And so here I have in the example that I had done, hold on just a second, I have to get something else out of my way here. There's my screenshot I picked for this 5-kip 36 over 247. 36-inch, a lighter 36-inch beam was acceptable for me at that go around with it. And then you can also include those actual criteria that were generated by your calculator. And like I said, you're not representing this as to be any kind of factual analysis. This is just you thinking about what was involved in this as a way to have a dialogue with the structural engineer. and he could point out that the loads are really much heavier than this, that your analysis and your place you picked for the critical load would be too much. But all of that's fine. It's really just leading you towards a better education about what you want to, I guess, be prepared for when you have a meeting with your engineer. And I think he would respect you for having at least looked at some of these issues that are involved with it. One other thing we'll do next is to look at the idea of the load on the vertical column.